Welcome back in this video series. We are still on molar quantities in a mole concept. I can see we are smaller at these nice balloons here. Yes, LearnRite, that is what we want to do. You see the illustrations, you see the demonstration, and it paints a permanent picture on your mind so that you remember whatever we said in this video or these lectures. Today, what we are looking at is molar volume. Molar volume simply means we are going to look at the volumes of 1 mole of all substances, particularly when we are going to limit ourselves to gases. Avogadro, a physicist and a chemist, in fact, did a lot of work on all these figures and constants that have been accepted generally as laws in this in science. We have something called the Avogadro's Law. Avogadro conducted a number of experiments on gases, and in his experiments, he proved to the whole world that at a constant temperature and pressure, the volume of all gases, provided the number of molecules are the same, the volumes are the same. I repeat, he proved to the whole world and became generally accepted by the scientific community that if you had at the same temperature and pressure, where you are not changing the temperature, you are not changing the pressure of the system that he's working with, the volume of all gases contain equal number of particles and equal volumes. Okay? Equal volumes of all gases contain equal number of particles. Or you could turn it the other way around. Equal number of particles will always occupy the same volume if temperature and pressure are kept constant. If you keep T and P constant, V was always equal to number of particles, let me say N. Remember, we have defined any number of particles of any substance as what? As N. So here we are talking about gases. Okay? Therefore, at a particular temperature and pressure, it means that 1 mole of any gas, which will contain 1 mole of any two gases, A and B, remember, will contain the same number of particles. If the temperature and pressure are kept constant, should also have the same volume. Do you agree with that? If I have gas A and I have gas B, at the same temperature and pressure, if I don't alter these two factors, then VA will be equal to the volume of A will be equal to NA, and of course VB will be equal to what? NB. Let me illustrate with these balloons. I'm assuming that these volumes are equal. If temperature and pressure are constant, the number of particles here should be equal to the number of particles here at the same temperature and pressure, as long as these volumes are equal. Now, if you choose 1 mole of each of these particles, which presupposes that their ends, that is their capital N, number of particles, here will be 6.02 times 10 raised to the power 23, will mean that they will all have a certain volume. And this volume, Avogadro chose to call it molar volume. Why is he calling molar volume? He's calling molar volume because it is the volume occupied by 1 mole of that particular gas. Okay? And for all gases, if you bring the same number of particles in the same system at the same temperature and pressure, they should occupy the same volume. So if this is carbon dioxide, if this is ammonia, irrespective of their molar masses, for the particles, you know, they will move and occupy this volume of balloon, and ammonia will move to occupy this volume of balloon, carbon dioxide will occupy this volume of balloon, as long as their particles, number of particles in there are the same. However, this balloon, the size here, indicating a smaller volume, means that the number of particles there will not be equal to the number of particles in any of these two. In other words, if I said this was carbon dioxide, the number of particles at the same temperature and pressure, the number of particles that will be in this volume here, because it is smaller, if you counted them, it will not be up to the Avogadro's constant. But if it were to be up to Avogadro's constant, then of course it will also expand to have the same volume. That is what we mean by molar volume. Molar volume, I repeat, is simply the volume occupied by 1 mole of any gas at a constant temperature and pressure. And this volume is what we call the molar volume, Vm. The constant temperature and pressure under which chemists do all their experiment is called STP, standard temperature and pressure. They call it STP. And the temperature is known as 273 Kelvin, and the pressure is 1.03 times 10 raised to the power 5 Newton per meter squared, or 1 atmosphere. This is the same as 1 atm. Okay, so in chemistry we seen STP at STP. It simply means at standard temperature and what? Pressure. All experiments are done with reference to that particular temperature and pressure. And various figures have been defined in relation to this temperature and pressure. And so if you do the experiment and measure something relative to 1 mole, then you say at STP, molar this. So molar volume, that is Vm, is in relation to STP. And he says that all gases, it doesn't matter the volume or molecular size, all gases will occupy a certain volume called the Vm. And the Vm at this temperature and at that pressure, what figure is the volume? The volume has been determined to be 22.4 dm cube, isn't it? 22.4, yes, dm cube. This can be changed because it is volume. It can be changed into several other volumes depending on the unit you are using. 22.4 dm cube is the same as 22,400 cm cube. Okay, which is also the same. Dm cube is the same as liters. It's also the same as 22.4 liters. And when we have cm cube, we can also, for this cm cube, we can write it to be 22.4 times 10 negative 3 meter cube. If you are converting the meter cube, if you are converting the dm cube or the cm cube to meter cube, we are dividing it by 1,000. And so if we divide this figure by 1,000 and you get this, okay, the unit must also divide by 1,000, and that becomes the meter cube. So these are the figures that we use. So molar volume is the volume measured for 1 mole of all gases at standard temperature and pressure. At standard temperature and pressure. Standard temperature and pressure has been agreed on by the scientific community to be 273 Kelvin for the temperature and 1.03 times 10 raised to the power 5 Newton per meter squared pressure, which is the same as 1 atmosphere pressure. Of course, it is the same as 760 millimeter mercury. 760 millimeter mercury. These are the units of pressure. All these are the same. So when you are doing any calculation, other units are in meter cube, are in newtons and meter. Make sure that you convert your pressure from wherever to this. If it is in atmosphere, convert your pressure into atmosphere. And if it is in millimeter cube or whatever, we have to know how to convert it. But mostly we'll be using this because most parameters are measured in meter. So that if you see that there's meter cube, quickly convert it to meter cube. So that this and this will be the same, then you can do your calculations out. So that is what we mean by molar volume. So again here, let's derive our formula. If at STP, 1 mole of any gas, 1 mole gas occupies what you call the VM, then any moles, n mole, should be able to occupy any volume V. So again, our n over 1 equals to V over Vm, which gives us n equals to V over Vm. Again, a formula that we use in calculating various parameters. If you are given a molar volume, you are given volume, or you are given number of moles. So you see how number of moles, that is amount of substance, in featuring in all the parameters that you have defined. First, we define n equals to NL. We again define n equals to m over m. That is in terms of molar mass. We have defined n equals to V over Vm. So all these are ways of determining amount of substance, the mole. So that is on the molar volume. Let's see if we can do some little calculations on this. Yes, look at page 44, example, that calculate I, amount of substance, RI, mass of gas, and RRI, number of molecules of gas in 2.8 dm cube of carbon dioxide at STP. 2.8 dm cube of carbon dioxide at STP. Then they have given you Vm, that is the molar volume, to be 22.4 dm cube. Carbon is 12.0, oxygen is 16.0. So that is the question. So the first one, it says calculate I, amount of substance. So we are going to look for N. We're looking for N. That is what we are looking for. What is the information given out there? It says from 2.8 dm cube of carbon dioxide at STP, molar volume is given. So we have V given as 2.8 dm cube. The gas we are talking of here is carbon dioxide. And then in the question there, your Vm is given as 22.4 dm cube. It will always be given. So if you are looking for N, it's simply saying that N equals to V over Vm. This gives us our V is 2.8 dm cube. And then the Vm you know is 22.4 dm cube is per mole. That's molar volume, so always per mole is attached. So if I divide this figure by this, what figure I get? The dm cube here will cancel dm cube here. Per mole is down there as a denominator. It goes up to become mole. So whatever figure I get from this, 2.8 divided by 22.4, I get my answer to 1.25. 0.125. 0.125 mole. The next question, II, says mass of gas. Once I've got the moles, and once I know the substance carbon dioxide, I'm able to calculate the mass of gas, isn't it? Okay, so that is from the first order formula. I want mass of gas, M. I know N. So what formula can I use? I have to use my N equals to M over molar mass. So here, I want my M. It means that my small m, that is the mass, equals to my N times capital M. This will give me 0.125 times the molar mass of carbon dioxide. I'll have carbon is 12 plus oxygen is 2 oxygen atoms, so 2, and oxygen is what? 16. So I have 0.125. This is 32 plus 12 will give me 44. So 0.125, this is mole, and this one is gram per mole. If I want to put them there, this is mole. Let me write it well. 0.125 mole, of course, times 44 gram per mole. So again here, my gram per mole will cancel. And then the mole, it will cancel the mole. So the answer I get will have the unit gram. And of course, the answer there is 5.5 grams. 5.5 grams. The third part of the question says, would you find number of molecules of the gas? Number of molecules. Number of molecules, what is it? Is what? Capital N. And capital N is what we are looking for. We know that N equals to small n L. L was given. So simply, our small n was 0.125 times, that will give us times 6.02 times 10 raised to the power 23. Remember, this is mole and this is particles per mole. So the mole will cancel the per mole and you get what? Particles. So if I multiply this by this, I think the answer 7.525. 7.525 times 10 raised to the power 23 is molecules of carbon dioxide. So put here molecules. That's all. That is how we solve these questions. It is not difficult at all. Just remember all the formulae, but understand how the formulae came about. So even if you forget the formulae, once you understand the concept, you can derive the formula yourself. Chemistry, we say in LearnRite, it is a fun game. We don't just give you the mechanical formula for you to chew and go and pour. When you get there, you have forgotten, you are not able to reproduce what you have chewed. We give you the concept, you apply the concept, and you understand it. This last concept here, molar volume, is from Avogadro's experiment, who says that at constant temperature and pressure, the number of molecules of all gases should occupy the same volume. That is it. So thank you once again for staying with us. I hope you enjoy these lectures. Come again with me to the next video. Very interesting video, of course, it will be. We'll look at the Avogadro's, we'll look at the Faraday's constant, and of course, delve deep into how to form solutions. All that we are doing is just giving the concept, the parameters that will help us understand our solutions when we begin to really do practicals in the laboratory. Don't miss out. LearnRite, always in the business of making you learn in the right way. Thank you.